Okay, well, good afternoon. So we're still in the chapter on entropy, and we're now specifically talking about what's called isentropic efficiency for steady flow devices. Before we get into that, just a comment or two on the homework that's been returned to you. First of all, remember that this is the last homework set that you're going to actually be turning in. I gave you the homework from really, it's sets 9 and 10, the problems from chapter 7 and 9 at the very end of class last time. I kind of forgot until one of you reminded me of that. So I had put this up on the board at the very end last time. If somebody, left really quickly last time or left a few minutes early, then you certainly want to get that from somebody else in your group. Anyway, I will post the solutions by Monday. They'll be up there for a full week before you take your final exam. You're probably aware, not that you want to hear this, that your final is going to be a week from Monday, March 13th at 11:30 in the morning. And I assume we'll just do it right here in this classroom, unless we hear otherwise. Let me also tell you well in advance that the format is going to be the same as the second midterm. So it will be, closed book, closed notes exam, except you'll be allowed to use a 3x5 note card, and you'll also be able to use the property table handout that I give you or that you bring yourself. We'll talk more about that next week, but just give you a heads up. And even though I'm not having you turn in the homework from next week and this week, you're still responsible for it, and you will definitely be getting at least 1 or 2 problems dealing with the material that we've covered since the second midterm. And of course, the second midterm was just last week. Well, I guess it was this week technically, but it covered through last week's material. So, don't let yourself fall behind just because the homework is not actually to be submitted. You definitely want to do it in order to do well in the final. All right, and then regarding the homework that was just returned to you, I think the biggest problem that I saw were students that were just using Q over T in order to find an entropy change. Now, you can only do that if it's an isothermal process, right? If it's isothermal, then we know that the integral of delta Q over T for the whole cycle is Q over T. In fact, I should say that it's for the isothermal reversible process. That's really the only time you can use this particular equation. Now, there were, 2 or 3 problems in this homework set that's been returned to you where you did have a problem that was both reversible and isothermal, so this is perfectly accurate. However, for most of the problems, you would just use the entropy data that exists within the property tables. If you knew that you had a particular process between some point 1 and some point 2, you would just look up the entropy at state points 1 and 2. Or if we had something like an ideal gas or a solid or a liquid, you would use the equation, that includes a natural log of the temperature ratio and perhaps some other terms. But you'd use that for those types of problems. You really only can use this, again, if it's a process that's reversible and isothermal. And again, only. Otherwise, you're just going to be using the data from the tables. So that was really the biggest error that I found. Those problems were generally short. Mostly they were very much like the first law problems we saw in chapter 4 and 5, but again, they talked about entropy here as well. All right, so now let's get back to what we're talking about now, which deals with isentropic efficiency. Sometimes this is called adiabatic efficiency for a steady flow device. Now, specifically, we're talking about pumps, turbines, and compressors, right? This is what we talked about last time. And this new term has been defined for you called isentropic efficiency. It has nothing to do with the thermodynamic efficiency, right? The isentropic efficiency is the relationship between the actual amount of work or power that is done or required by that device to the ideal amount of work or power that would be required by that device if it were indeed an ideal device. And in this context, ideal means isentropic, right? No change in entropy. And that's why we call it the isentropic efficiency. We're calculating the relationship between the work for the real process, the actual process, compared to the work for the isentropic process, that is the ideal process. So we found last time that for the turbine, the isentropic efficiency is eta sub t, and this is going to be the actual over the ideal work, and the actual over the ideal work can be written in many different ways, right? We could write it as total work. We could write it as work per unit mass. So we could write the actual work per unit mass over the ideal work per unit mass. We can write it as the actual power over the ideal power. They're all essentially the same, right? For a pump and a compressor, it's a little bit different. We're going to use A to P for pump. We'll use A to C for compressor. But what we would note here is that it's now defined inversely. It's the ideal over the actual. So ideal work over actual work. Again, this could be work per unit mass. It could be work per unit time, which we call power. They're all just different versions of exactly the same relationship. Most of the time, we're going to use a relationship that involves the work per unit mass. Okay, it's going to be the easiest for us. That's generally what we're going to be utilizing in this class. Keep in mind that in the real world, things are not isentropic, right? Isentropic would imply reversible, adiabatic, but real pumps, turbines, and compressors aren't reversible. There's losses, right? There's friction, various forms of friction, and other losses that we're not going to discuss right now. But we would expect that the actual amount of power that we're going to get out of a turbine isn't going to equal the amount of power that is lost by the fluid moving through the turbine. The fluid's going to lose some energy to create work, but there's also going to be some energy that's lost in order to just overcome friction. So the actual amount of work is different. It's actually less than the ideal amount of work because of these losses. Pumps and compressors are the opposite, right? They're work input devices, and when we provide work in, not only do we have to provide some work in to simply energize the fluid that's moving through that pump or compressor, but we have to add a little extra work in to overcome the friction associated with the fluid or the mechanical components in that particular device. So the actual amount of work in this case that is required ends up being greater than the ideal amount of work that would be required. So as such, we have inverted definitions with regards to the turbine compared to the pump or compressor. But that's to be understood, right? The turbine produces work, the pump or compressor require work, and it's because of that we have these definitions. And note that the maximum is 100%, right? If it's a truly ideal pump, turbine, or compressor, then the efficiency is 1.0. If it's an actual device, well, clearly the efficiency has to be less than 1 or less than 100%. So these numbers are always less than 1. Now the question is, how do we utilize this? What's our basic approach here? And let's think about it this way. It's pretty easy for us to determine the ideal amount of work associated with a device. We would note that, let's say we have a turbine, well, it could be a pump or compressor. We know the inlet conditions of that turbine. We typically know the outlet conditions from that turbine. At the very least, we know the pressure. After all, a turbine is part of a power plant or some other system. We know the various thermodynamic properties throughout. What we don't know is actually how much work will be produced. Well, what we do is we first assume that it's ideal. We calculate the WS term, and then we simply factor in the isentropic efficiency, and that gives me the WA term. And the isentropic efficiency for most problems is going to be given to you. When you buy a pump, turbine, or compressor, you will actually get a performance characteristic curve, a map we might call it, that comes along with that device. We know exactly what the efficiency is because the manufacturer of that device has calculated it for us. I mean, they've built their prototypes. They know what's being sent out to their customers. They've run it in their test facilities. They know what that efficiency is. That's something that's going to be given to us for all of our problems. Now, there may be a problem or two where one might have to estimate it, but for the most part, that's a given. So that brings us then to, well, then how do we utilize all of this? So let's just move on. And again, I want to talk about the turbine and the pump and compressor simultaneously, but let's start by looking at the turbine. And let's just first of all note that for these types of problems, we're always going to assume that it's adiabatic. In other words, no heat transfer, which makes sense, right? In the real world, your mechanical devices are going to be well insulated. You don't want to lose heat to the surroundings, so you insulate them, and that really minimizes the heat loss to the surroundings to the point where we can neglect it. So we're going to assume that it's adiabatic. We're also going to assume that there's no significant velocity changes, or that the velocities are low, and we're going to assume there's no significant height change. As such, the kinetic and potential energy are going to be 0. Well, the changes in kinetic and potential energy are going to be 0. So if we look at the first law, and this is certainly one of those single stream steady flow devices, you go through the mathematics and you end up with minus W equals H2 minus H1. And again, this is written on a per unit mass basis, right? The Q term is gone. The kinetic and potential energy terms are gone. This is all that's left with regards to our first law. Okay. Now, you know, a couple weeks ago I would have made sure I always wrote down the Q terms, the delta kinetic energy and potential energy terms. I don't think we really need to do that anymore. Hopefully it's understood. Yes?
This one's on a per unit mass basis.
Right, so that's a lowercase letter w, and those are just the specific enthalpies. I mean, I could write it as a total basis, then I would have capital W and a mass times delta H, or I could write it on a flow basis, W dot or minus W dot equals M dot times H2 minus H1. There's different forms of the same equation, but this is the form that's going to be most useful to us here in this section. Now, let's illustrate what this would look like on a TS diagram. So let's say we have a TS diagram. Now, I don't know exactly where I am on the TS diagram. Let's say we're either in the vapor section, you know, superheat section, or in the compressed liquid section. But in either case, we're going to have constant pressure lines that angle upwards. And let's say this is the maximum pressure, the upper line, and this is the minimum pressure, the lower line. So this says P max and P min. And we're going to enter the turbine at the high pressure. As it passes through the turbine, it's going to give up energy, the pressure is going to drop, and we're going to end at point 2, which is down here on the lower pressure line. The question is, where's point 2? If we assume that it's the actual process, then we're going to use H with a subscript 2a. In fact, I shouldn't even write H at this point. We're going to use did it again. We're going to use 2A as the discharge from this particular turbine. If we're looking at the ideal case, remember ideal means isentropic, then I'm going to use 2S. Again, S would represent the ideal. And now we can go back to the diagram here and say, well, where is the actual versus where's the ideal point 2? Now, this is a TS diagram, right? So in the ideal case, there is no entropy change. Point 1 and point 2S would have to be in the same vertical line, so 2S is really down here. On the other hand, in the actual case, there's going to be losses. We're going to end up still discharging from the turbine at the same minimum pressure, but the entropy is going to increase. So the actual point 2A is going to be over here somewhere. Now, when you show this on a diagram, I would always show a dotted line or a dashed line going from point 1 to point 2S, because quite frankly, that doesn't really exist. There's no ideal turbine. This is just an analytical tool of ours. We're assuming that it's an ideal turbine so that we can get the ideal enthalpy change, which represents the ideal work per unit mass, right? And then we're going to apply the isentropic efficiency equation that was presented above to get the actual enthalpy change, the actual point 2A. So 1 to 2S is a process that never really occurs, but we use it for analytical purposes, so I'm going to show it as a dashed line. The actual process goes from point 1 to point 2A, and as such, I'm going to show that as a solid line. Now, with all this in mind, what would be, therefore, our actual work or our ideal work terms? Well, if we just go to the general equation above, in the actual case, we're going from 1 to 2, A. So I would just note that minus W is H2A minus H1, or W is H1 minus H2A. So that's the actual work. The ideal work, well, we're still assuming what we've assumed above. It's still adiabatic. Clearly it's adiabatic and reversible. It has to be if it's ideal. And we get the same equation, but this time it's going to be H1 minus H2S. So ultimately, the equation for the turbine's isentropic efficiency, which is our actual over ideal work, is really just H1 minus H2 actual over H1 minus H2 ideal. Again, S for entropy, S for ideal, S for isentropic. So this is the equation that we would be solving for. Now, what would be, what would be the general method of solution? What would be a typical problem? In a typical problem, we're going to know state 1, and we're going to know one property, usually the pressure at state 2. Okay, so state 1 is going to be known. We know what the state is of the steam coming out of our boiler that's about to go into the turbine. We know that. We know the pressure that the condenser operates at. It's really going to be a function of your heat sink. That pressure is going to be known to us. P2 is a known quantity. With that information, we should be able to figure out the actual work, right? So if we know state 1 and one property at state 2, well, we do the following. At state 1, we just go into our property tables, and we're going to look up H1 and S1. And then at the two known properties at state point 2S, so in other words, at P2 and at S2S, and noting again that we're assuming that S2S is the same as S1, right? This is the isentropic process. So again, we have two thermodynamic properties. They're both intensive. We know the state. So at these values, we'll now look up the value of H2S. And then lastly, we just apply the isentropic efficiency equation. There's only one unknown, right? And that's H2A. So the process is really pretty straightforward, right? If we assume that it's an isentropic process, just like we looked at earlier in the week and last week, we just say that, well, S2S equals S1. That gives me H2S. We apply the efficiency equation. That gives me H2A. And that's really all there is to it, right? Now you can just go back to the work equation, and you can say that the work per unit mass is simply H1 minus H2 actual. So that's the actual work that's produced by this turbine. I'll give you an example problem here shortly. All right, so that's how we analyze the actual turbine. Sounds straightforward enough. Let us look at the compressor and the pump. Okay, so for a pump and compressor now. Okay, so first of all, we're going to do the same thing that we had done for the turbine. We're going to assume that it's an adiabatic device. Again, it's going to be well insulated. The heat loss is going to be minimal. We're going to assume that there's no change in kinetic or potential energy. So if we look at the first law for a single stream steady flow process, the heat transfer term is going to go away. Kinetic and potential energy terms are going to go away. We basically get, well, it's the same general equation that we had above, right? It's just minus the work equals H2 minus H1. Now, let's note that often we'd be interested in the absolute value of this. We'll note that H2 minus H1 is going to be a positive term. We're compressing, right? So the outlet is going to have a greater energy than the inlet, so this is a positive term. Often we're interested in just the absolute value. So the absolute value of the negative of the work is still just H2 minus H1. But often that's what we're going to be interested in, okay? And now what we want to do is we want to look at a little diagram, and then just like before, see what we can do to find the work terms. Okay, so we have this TS diagram. Again, I'm just going to show a maximum and a minimum pressure line. We're going to start at point 1. So, you know, this could be in the superheated vapor region, and we're dealing with a compressor. This could be in the compressed liquid region, and we're dealing with a pump. But in either case, we have a pressure increase as we go from the lower to the higher pressure, and we move vertically upwards. We'll again note, like we did before, that point 1 represents the known inlet conditions to this pump or compressor, and that at the outlet we have really two possibilities, right? If we assume that it's an actual pump or compressor, then we're going to again use 2A. If we're assuming that it's an ideal, which means isentropic, then we're going to use 2S. So the ideal process moves vertically upwards from point 1 to 2S. And again, we're never really going to create this particular process. This is just an analytical tool which allows us to determine the ideal amount of work that could be produced, that could be required if indeed this were an ideal compressor or a pump. But it's not, right? In the real world, you'll still discharge the compressor or the pump at that same maximum pressure, but it's going to have a higher entropy, right? There's going to be losses, and you're definitely going to end up at a point 2 actual that's got a higher entropy than 2 ideal. So we'll show a solid line from 1 to 2A. That's the actual process. And then we will look at the equation. So the equation for the compressor or the pump's isentropic efficiency is the ideal over the actual. Again, we're just going to use magnitudes or absolute values, if you will. I mean, it doesn't matter. If we don't use absolute values and we actually use a negative associated with required work input, the negatives are going to cancel in the numerator and the denominator, and we'll get exactly the same result anyway. But just by convention, we use absolute values. So this is then going to be the ideal work, which will then be H2S minus H1 over the actual work, which is H2 actual minus H1. So the typical problem is going to be just like the typical turbine problem, and it's this equation that we're going to have to utilize here. Yes?
H1 minus H2?
No, because, I mean, if we did H2 minus H1, that would be a positive number, but the negative of that tells you that the work is negative. It means work input is required. But I'm just going to find the absolute value of that. So even though I know work input technically is a negative number, I'm using the positive absolute value, which would be H2 minus H1. Yes?
So for the turbine, that one would be H1 minus the H2.
Right. Nothing has changed. My turbines, point 1 and point 2 are different, right? For the turbine, we had a higher pressure going in and a lower pressure going out, and thus a higher temperature going in versus out. Here now, when we're dealing with the pump or compressor, we have the higher outlet conditions rather than the higher inlet conditions, higher pressure and temperature. So as such, your enthalpy, the enthalpy difference is going to be different, right? The enthalpy is going to drop for the turbine, but the enthalpy is going to rise for the compressor. And again, if we use absolute values, then all that gets taken into consideration. All right, so what would a typical problem be? Okay, so let's deal with the compressor first. Exactly the same as for the turbine. Exactly the same. We're going to know the inlet state. We're going to know one property at the exit state. We go into our property tables at state 1 and find the enthalpy and entropy. We say S1 equals S2S. At S2S and at P2, we find H2S. We then apply the efficiency to get H2 actual, which gives us the work. There's no differences at all. So for the compressor, it's the same typical problem as for the turbine. So everything that was discussed above is certainly going to apply here. However, for the pump, things are ever so slightly different. You may recall that we also covered last time the whole idea of steady flow reversible work for a incompressible fluid. In fact, we didn't cover it so much as me just derive a very, very quick equation and say this is something we're going to have to use whenever we're dealing with a pump that is undergoing an ideal process, an adiabatic reversible process. Isn't that such a process? Isn't the process for the ideal pump work, this would be H2 minus H2S minus H1. Can't we also say that this is a specific volume times the pressure difference? Okay. So this is what we're going to use, and this comes from the material from last time. The fact is that the ideal enthalpy change equals the specific volume times the pressure change. Okay, so maybe I'll just put from last time. Okay. So that does ever so slightly change my efficiency equation, doesn't it? So the pump's isentropic efficiency, it's still the ideal over the actual work. I mean, that doesn't change. But the ideal work, instead of being H2S minus H1, we now have as V1 times the pressure difference, P2 minus P1, and then divided by H2 actual minus H1. So this is the equation we would use for a pump. And it really doesn't change things a lot. If we look at a typical problem again, we still know state 1. That doesn't change. We still know one property at point 2. Usually it's P2. So, I mean, that doesn't change. The only difference is that when we finally go into our property tables at state 1, we don't need the entropy. Okay, let's keep in mind that the reason we do all this anyway is because we don't have good compressed liquid tables. If we had good compressed liquid tables, which would be associated with a pump, then we would use a methodology exactly the same as we talked about for the turbine, exactly the same as it would apply for the compressor. But we don't have good compressed liquid tables, so we have to make these kind of approximations. And we would note then that what we really need is a specific volume at point 1, as well as the enthalpy at point 1, right? So we're going to look up H1 and V1. And then once we have that, then we just directly apply the pump's isentropic efficiency equation. And you can see that there's only a single unknown, right? Whoops, H2 actual. We apply this isentropic efficiency equation, the same one that's written above. The only unknown is H2 actual, right? So we get the actual enthalpy, and then of course once we have the actual enthalpy, then we can find the actual work, right? It's just the difference between H2 actual and H1. So again, pretty straightforward, not a significant difference compared to the compressor or the turbine. It's actually a little bit easier this way because it avoids having to find entropy data and using S1 equals S2S and then the inevitable interpolation, getting data out of our tables. So any questions? Good. Let's look at an example problem. By the way, I don't want anybody to overthink these problems. They're not that difficult. They're very, very similar to the first law problems that we saw previously. And remember that we're specifically dealing with steady flow devices. So it's chapter 5 material dealing with the first law. And in fact, we're only dealing with single stream steady flow devices, right? We're only dealing with a pump, turbine, or a compressor. So it's really a subset of the steady flow problems. So if we could have the computer, we're going to look at problem 124 from your edition of the textbook. Okay, it says addition 8, at least it's supposed to. All right, so here's the problem, and let me just read it. So we have refrigerant 134A that enters an adiabatic compressor as a saturated vapor at 100 kilopascals and at a rate of 0.7 cubic meters per minute, and it exits at 1 megapascal. If the isentropic efficiency of the compressor is 87%, then determine the temperature of the refrigerant as it exits the compressor and the power input. Also show this on a TS diagram relative to the saturation lines. All right, so that's our problem. We have a compressor that uses R134A. As usual, we'll use 1 and 2 to represent inlet and exit conditions. We know that the pressure at 1 is 100 kilopascals. And we also know that this is a saturated vapor. And then the exit, we know the pressure. So P2 is 1 megapascal. Oh, we're also given the volumetric flow rate. In fact, the volumetric flow rate was given at the inlet, so this really needs to go over here. V dot 1 is 0.7 cubic meters per minute. Okay. We're given the isentropic efficiency of the compressor as 87% or 0.87, and we want to find the exit temperature, T2. And I should really put T2 actual now, right? They ask for the exit temperature. The author rarely uses the word actual exit temperature, but we just know that there's really only one exit temperature, right? It's 2A. 2S doesn't exist. It's a tool we use. So if it asks for the exit temperature, it's asking for the actual exit temperature, not what would the temperature be if it were an ideal compressor. That's not what the author asked. Anyway, it wants us to find the power input. Yes, I'm sorry. Okay. All right, so this basically is a setup for the problem. Maybe I'll just show this on a TS diagram right at the beginning. And it asks relative to the saturation lines. We know that there's both a minimum and a maximum pressure. Those are both given. In fact, Pmax is P2, Pmin is P1. We start as a saturated vapor here at state point 1. And to show this properly on the TS diagram, we should really show both point 2s, which is directly above point 1, and we should show point 2a, which is to the right of point 2s. Well, above and to the right of 2s. So, I mean, that should be obvious. We start as a saturated vapor, and when you compress, you're obviously increasing the pressure, so the lines go upwards. And this is consistent with the diagram that I had just put into the notes here. So what is the methodology? What are we trying to find? Okay, first of all, in all problems of this type, we would be neglecting any kinetic and potential energy changes. They also tell us that it's adiabatic, right? Now, they didn't have to do that because, quite frankly, all of these problems that involve isentropic efficiencies refer to adiabatic reversible devices, so they're all adiabatic. We're only looking at the ideal versus the actual, but still adiabatic process. So the heat transfer is going to be 0. And since they've asked for the power, then I'm going to write my first law in terms of rates. So first law, single stream steady flow. For a compressor, well, I think we know what this is going to be. The work per unit mass actual is just going to be, and again, this is our magnitude. This is just going to be H2 actual minus H1. So ultimately, that gives me the work per unit mass, but I need it on a rate basis. So this probably isn't the best form. Let's just multiply both sides by m dot. So basically, we get that W dot actual. That's really W dot 1,2. Should I put 1,2? Should I put actual? Either way is fine, as long as you can remember that this is the actual power output. So this is going to be the mass flow rate times the actual work per unit mass, or just m dot times H2 actual minus H1. So this is going to be the magnitude of the work input, really the power required by this device. Okay, so with this in mind, what would be the proper approach? It's exactly the example problem that I was referring to, the typical problem I was referring to before, right? We know the inlet state, right? We know the pressure and that it's a set vapor. We know one property at the outlet, we know P2. We know the isentropic efficiency. So you just use your information at point 1 to find S1. S1 equals S2S. You go into your property tables at S2S and P2. You read off the enthalpy at 2S. And then you go to the isentropic efficiency equation for the compressor and find H2 actual, and then you can plug it into the equation above and solve for the power. So again, the compressor is the ideal over actual, so this is H2S minus H1 over H2 actual minus H1, and this is the equation that we're also going to have to use. So let's just go through the mathematics. So we might as well start by getting our property data. So at P1, saturated vapor, it's the refrigerant, it's the pressure tables, it's the SI units, so table A12. And we need H1, which is going to equal Hg. We also need S1, which is equal to Sg. So H1 is 234.44 kilojoules per kilogram. S1 is 0.95183 kilojoules per kilogram per Kelvin. We're also going to need a specific volume at 1. I mean, I didn't mention that earlier, but we're given a volumetric flow rate, and we need a mass flow rate. So the only way we ever convert from volumetric to mass flow rate is just to divide the volumetric flow rate by the specific volume. So we definitely need V1, right? So V1 is equal to Vg, and that's 0.19254, and that's going to be meters cubed per kilogram. And now, since we're given the volumetric flow rate at 1, we have to use a specific volume at 1 to get the mass flow rate. So we might as well just do that right away. So we have 0.7 cubic meters per minute. We divide by 60 seconds per minute. We further divide by the specific volume. And if we plug in all the numbers, we end up with a mass flow rate of 0.06059 kilograms per second. All right. So we have that information. Now let's find the information at state point 2. Really, it's 2S, not 2, right? So at P2 and at S2S, which equals S1, well, we don't know exactly, actually we do know exactly what the thermodynamic state is. We don't know the actual state, we know the phase, it's definitely superheated, right? So I don't have to do any kind of a test. I mean, we just know when you start with a vapor and you compress it, you end up with a higher pressure vapor. So we're definitely going to still be in, we're definitely going to be in the superheated region. I shouldn't say still. We start with a saturated vapor, we compress into the superheat region. So this is table A13. So we go into the 1 megapascal subtable. We read down to the appropriate entropy line. We find that it doesn't exist, right? That my value of entropy is between the values of entropy that correspond to the one higher temperature and the one lower temperature on this particular diagram. I believe you'll be between the 50 and 60 degrees Celsius lines on that 1 megapascal subtable. But nonetheless, by interpolation, which at this point you've probably done weekly for the last 2 months, so it's not hard to do anymore. We get H2S of 282.51 kilojoules per kilogram. Okay. So that's all the property data that we're going to need. We'll now apply the isentropic efficiency. So for the compressor, it's 0.87. And again, this is going to be H2S minus H1 over H2 actual minus H1. Just to save a little bit of time, we can solve this for H2S, and we end up with 289.69 kilojoules per kilogram. And now that we have the enthalpy at 2S, I'm sorry, we had H2S already. We're finding the enthalpy at 2A. This is the enthalpy at 2A. I apologize. So that's H2A, right? H1 is known, H2S is known, because we assumed that it was isentropic from 1 to 2S. So the only unknown is H2A. So we get 289.69 as the actual enthalpy. Now, we do need that in order to find the work or power, but let's just also find the temperature. Now that we know the actual enthalpy at H2 actual and at P2, well, we have to go back into the superheat table, table A13. This time you're going to interpolate on enthalpy in order to find the actual temperature, and we end up with the actual temperature of 56.5 Celsius, and again by interpolation. But nonetheless, that's how we would get the actual temperature. And then the last step would be to calculate the power. We know already that the actual power, which if you prefer, we can call it W.12, at least in magnitude. This is going to be H2 actual minus H1 times the mass flow rate. Oops, didn't leave myself room. This is going to be the mass flow rate times H2 actual minus H1. So again, I'll let you plug in the numbers on your own. If we go through the mathematics, we end up with 3.35 kilojoules per second, which is kilowatts. So there you have it. So in solving these types of problems, you need to know your inlet state, one property at the outlet. You first assume that it's an ideal, that is isentropic process, to get what would be the ideal enthalpy leaving that particular device. And then you say, well, but it's not ideal, it's actual, so then you apply the efficiency, and that gives you the actual enthalpy leaving that device, which then allows you to find the work. So these problems are certainly a little bit different. If this were a problem out of Chapter 5, I would give you the inlet and exit conditions, and you'd have to find such things as the power output. Here, we don't know the exit conditions. We have an efficiency, and we assume that it's isentropic, and then apply that isentropic efficiency to get those exit conditions. But it's not a whole lot different, really, than any of those problems that we saw for, well, single-stream steady flow processes in Chapter 5. Are there any questions then on this problem? Okay. Well, what comes next? There's always something that comes next, and you probably know what this is going to be. What if we don't have tables? Like, let's say we have an ideal gas, and we're interested in doing a similar problem. How do we do that? Well, we can't use the method I've described above because we don't have tables to use. So there's got to be some method which would allow us to use equations to find the relationship between inlet and exit conditions for both the isentropic process as well as the actual process. And that's exactly what we're going to do now. We're going to use equations. So we have all the equations we need, by the way. The only thing we haven't done is kind of coalesce it into one methodology. So let's look at that now. And we're specifically talking about ideal gases for these types of problems, for, well, isentropic efficiency for steady flow devices. Specifically, let's deal with ideal gases. And in fact, the only method we're going to look at is ideal gases with constant specific heats. Now, certainly, as you read through this material, it does talk about how you would use variable specific heats, and it talks about using things like the air tables, table A17, and others. You can neglect that. Just like we've done previously, we're always going to assume, at least for now, that the gases are ideal and that the specific heat is constant. So that way, an enthalpy change is going to equal Cp times temperature change. I mean, that's really what this is all about. If we assume constant specific heats, then it's very simple to convert from enthalpy change to Cp times temperature change. So that's what we're going to do here. Now, let us again separately look at the turbine versus the compressor and pump, and we'll see that there's actually, we wouldn't even have to look at a pump, would we? A pump moves a liquid. There's no ideal gases if we've got a liquid, so we're really only talking about turbines and compressors here, right? We're not dealing with pumps at all. So let's look at the turbine first, and then we'll look at the compressor. In fact, let me just start with a diagram, the same kind of diagram that we saw before. We have our max and our minimum pressure. We're going to enter the turbine at point 1. If it were ideal, we'd leave it 2s, but it's not ideal, it's real. So we have the actual discharge from the turbine at point 2a. We're still going to use the same equation for the turbine's isentropic efficiency. It's still going to be the actual over the ideal work, and I'll put it on a per unit mass basis because that generally is applicable to these types of problems. We know this is just going to be H1 minus H2 actual over H1 minus H2S. However, if we're assuming that it's an ideal gas with constant specific heats, then isn't the enthalpy change just equal to Cp times that temperature change? So this really becomes Cp times T1 minus T2 actual over Cp T1 minus T2 ideal. And in fact, if we're assuming constant specific heats, you're assuming the same constant specific heat for whether it's an ideal or a real process. So the CPs are going to cancel. And therefore, the turbine's isentropic efficiency is based solely on temperatures. We don't even need to know what the specific heat at constant pressure is. So this is the equation then that we're going to use for a turbine. Now you may say, what about the problem-solving methodology? Sure, I see now that the efficiency is a function of the temperature, and I can see that once I get T2A, then I can use Cp times T1 minus T2A, and that gives me the actual work, and then I can multiply by mass flow rate, that gives me the actual power. But the question is, how do we get to point 2s? We know T1, right? We're always going to know the inlet state. We're always going to know one property at the outlet state. We're going to have to assume that it's an isentropic process from 1 to 2s, but we're not going to just say S1 equals S2s like we did previously. We only do that when we have a table. Do we have an equation that applies to an ideal gas that relates temperature only, or maybe temperature and other properties that we might know, hint, hint, pressure? Do we know any equations like that that apply to ideal gases? Well, of course we do, right? Because we look back into the material that we covered earlier, and we would note that for an ideal gas that undergoes an isentropic process, didn't we find that the temperature ratio, and let's see, this would be T max over T min, so the temperature ratio T1 over T2 is going to equal the pressure ratio P1 over P2 raised to K minus 1 over K. Now this applies only for the isentropic process, so I can't just leave that as a 2, right? I have to put a 2s there just to remind myself that this applies to the isentropic process from 1 to 2s only. But this is how we're going to do it, right? This one equation takes the place of saying S1 equals S2s, and at S2s and P2 we can get H2s. This takes the place of all that. One simple equation allows me to go from point 1 to point 2s directly, and it's entirely in terms of what we know, right? We know P1 over P2. So that's the equation we're going to use for a turbine. And as you might expect, the equation for the compressor is going to be very, very similar. By the way, let me define one more term for you. This is simply called the pressure ratio. And the pressure ratio is P max over P min. And we use R sub P for pressure ratio. So as such, for the turbine, we could note that T1 over T2s is just equal to that pressure ratio raised to the K minus 1 over K power. So this is exactly the same as the equation above. It's just that we're going to now utilize this new term called pressure ratio. In some problems, you'll be given the actual pressure P max and P min. In other problems, you won't. You'll simply be given the pressure ratio. The fact is, you don't need the actual pressures, right? All you really need are the pressure ratios. To solve a problem like we did previously with a pure substance like water or the refrigerant, well, then it's not enough to just know the pressure ratio. We actually need the pressures at the inlet and at the exit. All right, so this allows me to find T2S. What about the other situation? What if we had a compressor? Well, again, not a whole lot different. I'll start with a diagram. We would note, again, that the higher pressure is P max, the lower pressure is P min. We're going to enter the compressor at point 1. If it were ideal, we would exit at 2S directly above, but it's not. We're actually going to leave at a higher entropy. Oh yeah, this is a TS diagram. In fact, this diagram up here was a TS diagram, but I forgot to put my T and my S, so that's not appropriate. You can't have a diagram with no axes on it. Well, you could, it just wouldn't be right. So here we have our compressor diagram. We do the same thing as we did before, right? Our compressor's isentropic efficiency is ideal over actual work per unit mass. So this is going to be H2S minus H1 over H2 actual minus H1. Again, these are the magnitudes. We know that the enthalpy change is equal to Cp times the temperature change. So Cp times T2S minus T1 over Cp T2 actual minus T1. Again, the Cp's cancel. And we end up then with an equation for the compressor efficiency. It's just T2S minus T1 over T2 actual minus T1. So this is how I'm going to find the isentropic efficiency for a compressor. And again, this gives me the same problem that I had above, right? We have the equation in terms only of temperatures. That's simple enough, but how do we get the temperature at 2S so that we can then apply this isentropic efficiency equation to get the temperature at 2A, the actual temperature at the discharge from this compressor? Well, we've got the same equation, right? It's still an isentropic process. We are still specifically dealing with ideal gases, and if we have an isentropic process, then we still have the same relationship as we had above. Now, I am going to flip it, however. I will note that since P2 is the maximum pressure and P1 is the minimum pressure, I'm going to write this now as T2S over T1 equals P2 over P1 raised to the K minus 1 over K power. So that equation still is certainly going to apply. And I've already defined the pressure ratio as P max over P min. Keep in mind that P max is P2 for the compressor, P min is P1. So this is still the pressure ratio, which is our P, raised to the K minus 1 over K power. So this equation is then the one that you're going to use for the compressor in order to get T2S. And again, once you have T2S, you'll know T1, right? You'll know the pressure ratio. K is just the ratio of specific heats for any gas. We just look up that data in table A1 or A2. Actually, I guess it's A2 for that data, right? So we have T2S. We apply the compressor's isentropic efficiency. That gives me T2A. We then note that T2A minus T1 times Cp is the enthalpy difference, which is the work per unit mass. We can multiply it by the mass flow rate if we need to get the power. So these problems are very, very similar then to the other problem, the turbine types of problems. Any questions on this general setup? Well, how about another example problem then? Yeah. Yeah, except now I'm going to start another example problem, so I kind of want that there. But yeah, I apologize. I should have had that done for the last 10 minutes or so as this was being developed. Yeah, I wish there was some way that I could turn the screens or something. Unfortunately, I can't. So, I mean, if you want, we could just switch screens. With the computer on the other side and the lecture notes on this side. That might make it a little bit easier for some of you to kind of catch up here. So I believe this one's out of the 6th edition. Yeah. Okay, so here we have a gas turbine, an argon gas turbine. And let me read this one to you. So first of all, this is 7-133 from the 6th edition of your book. Right. So let me read it. It says you have argon gas that enters an adiabatic turbine at 800 Celsius, 1.5 megapascals at a rate of 80 kilograms per minute, and exhausts at 200 kilopascals. So it kind of sounds like the previous problem, except that it's a gas, and instead of giving a volumetric flow rate, in this problem they give you a mass flow rate, but same kind of problem. It says if the power output is 370 kilowatts, determine the isentropic efficiency of the turbine. So this one is actually a little bit different. You'll still use the same relationships, but whereas the previous problem gives you all that thermodynamic property data and it gives you the isentropic efficiency so that you can find the power output. Actually, it was power input to the previous problem. This problem gives you that power and then asks you to kind of work backwards, if you will, to find the isentropic efficiency. But it's still the same kind of problem. So let's illustrate this one. We've got argon. The only method we have whereby we can solve a problem involving a gas is to assume that it's an ideal gas. Use the method we've just discussed. So it's an ideal gas. As usual, we'll let 1 and 2 represent the inlet and the exit. It's adiabatic, so there's no heat transfer. Because we're given power, then maybe I'll just put Q dot, since everything should be in terms of rates. We're given T1 as 800 Celsius. We're given P1 as 1.5 megapascal. We're given M dot 1. Actually, I'll just put M dot. These are all steady flow problems. So that's 80 kilograms per minute. I suppose we could divide by 60 to turn this into kilograms per second. So what's that? 1.333 kilograms per second. Is that right? That's right. Okay. We also have been given the exit pressure. So P2 is 200 kilopascals. We've been given the actual power that's produced by this turbine. So that's 370 kilowatts. And we're trying to find the turbine's isentropic efficiency. All right. So again, we're going to use the same kind of information that we used in the previous example, although this isn't the previous example. It's a little bit different. We are definitely going to have to use the isentropic efficiency equation for that particular turbine. Now, we don't have a lot of temperature information. There's different ways that we can find this, right? I mean, we could just say that this is the actual power over the ideal power. We could just easily say that this is T2 actual minus T1 over T2S minus T1. We'll use one or the other, but as for which one we're going to use, we'll just leave that open for the time being. We're definitely going to have to find a relationship for the isentropic process, so we'll note that T2S over T1, I'm sorry, I have that reversed, this is a turbine. We'll note that T1 over T2 is the pressure ratio to the K minus 1 over K. So that's certainly something that we're going to have to look up. That is, we're going to have to look up K, we're going to have to use this. And again, you can't just leave the subscript 2 as just a 2, right? This is either ideal or it's actual, and this only applies to the ideal, that is the isentropic process from 1 to 2. So that's the equation we're going to use. So if you think about it, there shouldn't be a whole lot more that we really have to do. Well, one thing, since we're given the actual power, then this is going to equal the mass flow rate times Cp times the actual enthalpy change, so T1 minus T2 actual. So this is something that we're going to have to use in order to find T2A, right? So now I think we have the problem set up. Let's think about it. We know the mass flow rate. We can look up CP. We know T1. We know the actual power, so we can just find the actual temperature of the discharge using this equation. Using the equation directly above, well, we know the pressure ratio. We can look up K. We know T1 again, so we can just look up, so we can just calculate T2S based on this equation. Well, that means we have T1, T2A, T2S. We can then just plug those into the equation above and get the isentropic efficiency. So it's these general equations that we're going to have to use. Let's just use them. So if we go into the appropriate property tables, A2, why don't we use A? By the way, there is no data for argon gas over a wide range of temperatures, so we're not going to use the average temperature. Of course, we don't know what that average temperature is anyway, so that's just as well. So from table A2 part A, we'll look up the value of K, which is 1.667. And we'll also look up CP, which is only for room temperature here, and that's 0.5203 kilojoules per kilogram per Kelvin. So now we can plug the information into this power equation below. So we get 1.333 kilograms per second times 0.5203 kilojoules per kilogram per Kelvin. And then the temperature difference we can do either in Kelvin or Celsius. It really doesn't matter, but we might as well do it in Kelvin since we're going to need to use Kelvin anyway eventually. I mean, we can't use this temperature ratio equation above unless it's in Kelvin, right? So this would be then T1, which is, let's see, 1073.15, and then minus T2 actual. And if we go through the mathematics, oh yeah, this equals 370 kilowatts, which is kilojoules per second, right? Anyway, we go through the math, and we get the actual temperature that leaves this turbine as 538.3 Kelvin. Now, we use the equation for the isentropic process in order to get T2S. So T1 over T2S equals a pressure ratio to the K minus 1 over K. So T1 is known. Again, we have to convert this into Kelvin. So we add 273.15. So 1073.15 over the unknown T2S equals the pressure ratio, which is 1500 over 200. These both have to be in the same unit, so I'll convert to kilopascals. And then K minus 1 is 0.667 over 1.667. So there's my exponent. And we solve this one for T2S, and we end up with 479 Kelvin. And now that we have that, it's a simple task to find the isentropic efficiency. Again, make sure that all your units are in Kelvin, although I guess technically it doesn't matter since we're only dealing with temperature differences. So as long as you're using the temperature differences, either in Celsius or Kelvin, you'll get the same results. We actually get 0.898, or if you prefer, 89.8%. Now, you could check this if you want. It never hurts to check your final work. We also know that the isentropic efficiency is going to be the actual power over the ideal power. We have the actual power because it's been given to us, right? 370 kilowatts. The ideal power would just be m dot Cp times T2S minus T1. So if we just plug that in from above, we have all that data, guess what? We get exactly the same result. Well, we should get the same result. If you get different results using different methods for the same problem, then you've clearly made a math error somewhere. But no math errors here. So are there any questions then? Yes?
Should the formula for efficiency be T1 minus T2A?
Yes. In fact, gosh, I wrote it incorrectly all throughout here, didn't I? I'm glad somebody saw that because I would have been oblivious, and then I would have found out later, and it would have been a problem. So yeah, if you could just cross this out, you're right. The actual is T1 minus T2 actual. It comes in at the higher temperature, and it's producing work, so it comes out at the lower temperature. So yes, this should absolutely say T1 minus T2A over T1 minus T2S up here above. This power equation's right. This this equation is right. Yes, so this should also, this should say, T1 minus T2 actual or T1 minus T2S. Okay. By the way, mathematically it doesn't matter. If you reverse both the top and the bottom, you end up with the same magnitude, but you'd end up with the negatives, and the negatives would end up canceling, and you get the same numerical result. But that doesn't mean that you want to use the wrong equation to get the right result. You want to use the right equation to get the right result. Anyway, I apologize for that, but that's okay. So any final questions on this material? All right, so that's it for today. Have a good weekend, everybody. Please don't forget to pick up your homework that was returned earlier. The solutions are already posted. See you guys on Monday.